Hey, welcome back to Leetcode Problem 35, search insert position. So given a sorted array of distinct integers and a target value, return the index if the target is found. If not, return the index where it would be if it were inserted in order. And you have to write this in O of log n runtime complexity. So looking at the examples, if our target is 5, we see here that 5 is in the second index, so it returns 2. Provided that the target is 2, in the second example, we would output 1 because 2 would be in the first index after this 1 here instead of this 3. And for 7, we can see here that it would be in the fourth index because it would come after the 6. So 0, 1, 2, 3, 4. So whenever you see a problem like this, even if it didn't tell you to write this in O of log n runtime complexity, you should be recognizing it as a binary search problem, right? Because key words here to pay attention to is that the array is already in order and you're going to be searching. So when you're searching for something, a binary search is always very useful. It helps a lot if your input is already sorted. If it's not, a common thing to do is to try and sort your input. That way you can use it, but our input's already sorted for us. The only thing that's a little bit different about this problem is if the target doesn't exist, return the index where it should be if it did exist, right? And so what does that mean? It means that let's still just run a binary search. What happens when binary search doesn't find the target? Well, it actually ends, and then depending on how you do it, your pointers would already be pointing to the position where it should exist in. Here I'm going to use a left and right pointer and just run a binary search. If we come out of that binary search and we don't find the target, we'll just return the left pointer that we started moving around. Because by the end of binary search, that's where our target would and should be. So let me just get started here. L r equals 0, and r is going to be the length of nums minus 1. And then let's write our binary search here. So while L is less than or equal to R, mid is equal to L plus R divided by 2. And in Python, we're going to do this floor division so that we get our division rounded down. Now, if nums at mid is equal to the target, if we find our target in the very middle, then we're just going to return mid, right, the index. Else if nums at mid is greater than the target. Well, what does that mean? If our nums, if our current number that we've calculated to be the middle of that search space is greater than our target, that means our target's on the left side, right? So if I had 1, 2, 3, this is kind of just like a refresher on how binary search works. If our target is 2, and let's say we calculate nums of mid to be, well, there's 1, 2, 3, 4, 5, 6, 7. 7 things, and we split that in half, right? So 7 divided by, or 2, the floor division is going to be 3. 0, 1, 2, 3. We see that 4, nums at mid in this case would be 4, which is greater than our target. Since this is sorted, now we know that our search range has now compressed to just the left side. So if nums at mid is greater than the target, that means that target resides on the left side, right? Potentially. That means that if it's on the left side, we should shrink our search to the left side. So r is equal to be mid minus 1. Because we're just going to split it in half and shrink the right side to the middle minus 1 because we've already considered up to mid, right? We don't want to consider it again. And then else, that means that if not, then the target resides on right side, right? So we would do the opposite of this. If we shrank R, then we're gonna move L up, right? So mid plus 1. And if we ever come out of this, if binary search ends, target does not exist in the list. So now we're just gonna return null. Let's run that. Great, that works. Let's submit. Very nice.